Concrete structures are known to be highly vulnerable, may it be to fissures, ruptures, and even to tensile cracking, due to varying forces being applied affecting the concrete's strength and structural integrity. Though concrete is recognized for its high compressive strength, its tensile strength determines the maximum amount of tensile stress that concrete can consider before failure. To measure the tensile strength of concrete, two test methods can be implemented. First is the split cylinder test. It is the standard test to determine the tensile strength of concrete in an indirect way. This test could be performed in accordance with IS Indian Standard 5816-1970. A standard test cylinder of concrete specimen by 300 mm by 150 mm in diameter is placed horizontally between the loading surfaces of the compression testing machine. The compression load is applied diametrically and uniformly along the length of the cylinder until the failure of the cylinder along the vertical diameter. The second method is the flexure test. It is a test to determine an unreinforced concrete beam or slab to resist failure in bending. It is measured by loading a 6 by 6 inch or 150 by 150 mm concrete beam with a span length of at least 3 times the depth. It is determined by standard test methods ASTM C78 or third point loading or ASTM C293 or center point loading.
Experimentation and observations were provided from split tensile strength test of concrete by engineers at Avera Dinesh. The main objective of the experiment is to determine the tensile strength of the concrete specimen using the split cylinder test method. The materials needed are the universal testing machine, cylindrical molds, specifically 100 mm in diameter and 300 mm in length, tamping rod, measuring cylinder, scoop and trowel, weighing balance, and two steel rods specifically 30 cm long and 16 mm wide. The first procedure is to measure 3.5 kilograms of cement, 14 kilograms of aggregate, 7 kilograms of sand, and 2.1 liters of water. Next is to apply oil on the cylindrical molds to easily remove the molded concrete. Third is the mixing process to make the concrete mixture. Fourth is to make a cup shape where the water will be added. After the mixing process, the mold is filled with the mixture in 3 succeeding layers, each compacted using the tamping rod. Next is using a cement trowel, finish and plane the surface of the mold. Then, let the mold dry for 24 hours. After 24 hours, take out the specimen from the mold. Then, submerge the molded concrete in water for 28 days. After 28 days, measure the weight of the cylindrical concrete specimen using a digital weighing scale. Lastly, set the specimen in the universal testing machine to be compressed in load increments until a vertical crack appears in the specimen.
Data gathered. Mixed proportion of cement, sand, and aggregate is 1:2:4. Cement 3.5 kilograms. Sand 7 kilograms. Aggregate 14 kilograms. Water 2.1 liters. Water over cement ratio 2.1 all over 3.5. Diameter of cylinder 150 millimeters. Length of cylinder 300 millimeters. Breaking load 100 kilonewtons. Computation. Splitting tensile strength formula is 2P all over pi LD, where P is the breaking load with the unit of Newton, L is the length of cylinder with the unit of millimeter, V is the diameter of cylinder with the unit of millimeter. Solving for the splitting tensile strength is equal to 2 times 100 times 10 raised to 3, since 100 kilonewton is converted to newton, all over pi times 300 times 150. The answer is 1.41 newton all over millimeter squared.
In the split cylinder test, the compression load from the machine was applied diametrically and uniformly along the length of the cylinder, causing the failure of the cylinder along the vertical diameter. Such applied load is distributed along the cylinder, reducing the magnitude of high compressive stress on application, allowing the concrete cylinders to split into two halves. Also, due to indirect tensile stress generated by Poisson's effect. Due to this compressive loading, an element lying along the vertical diameter of the cylinder is subjected to a vertical compressive stress and a horizontal stress. This loading condition produces a high compressive stress immediately below the loading points of the cylinder, and thus allowing for the tensile stress to act for about 1/6 depth, and the remaining 5/6 depth is then subjected to tension due to Poisson's effect. With the findings from the observation and experimentation, the concrete cylindrical specimen behaves as an elastic body with a uniform lateral tensile stress acting along its vertical planes, causing failure to the specimen itself.